Still talking about BJT, bipolar junction transistors. Now we move from the Class A distinctions to the Class B amplifiers. When an amplifier is biased such that it operates in the linear region for 180 degrees of the input cycle and then is in cutoff for 180 degrees, we call it a Class B amplifier. The primary advantage of a Class B amplifier over a Class A is that the Class B is more efficient. You can get more output power for a given amount of input power. A disadvantage of a Class B amplifier is that it's more difficult to implement the circuit in order to get a linear reproduction of the input waveform. As you'll see, the term push-pull refers to a type of Class B amplifier circuit in which the output wave shape is approximately reproduced at the output. Class B amplifier operation is illustrated below. For the case of the common collector amplifier, the Class B amplifier is biased at cutoff so that the current ICQ is equal to 0. The voltage VCEQ or VCE cutoff, it is brought out of cutoff and operates in its linear region when the input signal drives into conduction. So we can see it illustrated below with an emitter follower circuit. What makes it an emitter follower? Again, we don't have a resistor here, but we do have a resistor here. So we can see what they're talking about in terms of the input voltage here when the transistor conducts and when the transistor is cut off, and what the output should look like. In push-pull operation, a push-pull Class B amplifier using two emitter followers, this is a complementary amplifier because one emitter follower uses an NPN transistor and the other uses a PNP. So NPN, PNP, which conducts on opposite alternations of the input cycle. Notice that there's no DC bias voltage, so VB is equal to 0. Thus, only the signal voltage drives the transistors into conduction. Transistor 1 conducts during the positive half of the input cycle. Transistor 2 conducts during the negative half. So we can see that in the diagrams. When the DC bias voltage is 0, the input signal voltage must exceed the voltage base to emitter before the transistor conducts. As a result, there is a time interval between the positive and negative alternations of the input when neither transistor is conducting. As we can see in the diagram, the resulting distortion in the output waveform is called crossover distortion, okay, because we have no signal occurring in those places. To eliminate crossover distortion, both transistors in the push-pull arrangement must be biased slightly above cutoff when there is no signal. This can be done with a voltage divider and a diode arrangement. When the diode characteristics of diode 1 and diode 2 are closely matched to the characteristics of the transistor base emitter junctions, a stable bias is maintained. So you can see here we've added diode 1 and diode 2 into the base part of the circuit. Since R1 and R2 are of equal value, the voltage with respect to ground at node A, there's node A right here in the center, between the two diodes is half of VCC. So it's half of the source applied up here at VCC. Assuming that both diodes and both transistors are identical, again, they do this at the matching, at the manufacturing point to get them both from the same material out of the same batches. The drop across diode 1 equals the voltage base to emitter of Q1. So up here. The drop across diode 2 equals the voltage base to emitter of Q2 down here. As a result, the voltage at the emitters is also VCC divided by 2. And therefore, the voltage collector to emitter transistor 1 is equal to the voltage collector to emitter transistor 2 is equal to half of VCC as indicated. Because both transistors are biased near cutoff, the current C, the collector for the transistor, is equal to 0, or approximately. Under maximum conditions, the transistors 1 and 2 are alternately driven from near cutoff to near saturation. During the positive alternation of the input signal, transistor 1 emitter is driven from its Q point value of half of VCC to VCC. So from the half the value to the full value of VCC, producing a positive peak voltage ideally equal to the voltage collector to emitter. In practice, the peak voltage will be a little less than VCEQ. At the same time, the transistor 1 current swings from its Q point near the value of 0 to near saturation value, as shown. So we can see here where we get the maximum values. Capacitors are assumed to be shorts at the signal frequency, and the DC source is at AC ground. During the negative alternation of the input signal, transistor 2 emitter is driven from its Q point value to half of VCC to near 0, producing a negative peak voltage ideally equal to VCEQ. Also, transistor 2 current swings from near 0 to near saturation value as shown in diagram B. So we can see here in diagram B. Because the peak voltage across each transistor is VCEQ, the AC saturation current then is given by IC sat is equal to VCEQ by RL. Determine the ideal maximum peak values for the output voltage and current in the figure below. Notice how our diagrams are getting more and more complex and more things to consider in terms of what the current looks like from the collector to the emitter, from VCC to the output, across each of these pairs and at the inputs. The ideal maximum peak output voltage then, V peak out, is equal to VCEQ, which as we said was half of VCC. So in this case, VCC is 20 volts. We divide it in two. We have 10 volts as the peak out. The ideal maximum peak output current then, I peak out, is equal to the current C sat, which is VCEQ, this time by RL. So 10 volts by 8 ohms gives us 1.25 amps. Maximum output power. It's been shown that the maximum peak output current is approximately the current C sat. and the maximum peak output voltage is approximately VCEQ. The maximum average output power, therefore, then P out is equal to VRMS out times IRMS out. Since VRMS out is equal to 0.707 times the peak, we get 0.707 times the voltage CEQ. Likewise, for the current, IRMS out is equal to 0.707 times the peak current out, or 0.707 IC sat. Then the power out is equal to 1/2 of VCEQ times IC sat. Substituting half of VCC for VCEQ, then the maximum power out is equal to 1/4 of VCC times IC sat. The input power then comes from the VCC power supply and is the power DC, which is equal to VCC by ICC. Since each transistor draws current for a half cycle, the current is a half wave signal with an average value of IC sat divided by pi. Okay, there's our half signal relationship. So the power then is equal to VCC IC sat divided by pi. The efficiency then, the main advantage of a push-pull amplifier Class B over Class A is that the Class B amplifier has a much higher efficiency and can be used in higher power applications. This advantage overrides the difficulty of biasing the Class B push-pull amplifier to eliminate that crossover distortion. The efficiency of an amplifier is defined as the ratio of AC power to DC power. So efficiency, power out, AC divided by power, DC. The ideal maximum efficiency for a Class B amplifier is designated as efficiency max and can be shown to be a value of 0.785. Therefore, ideally, the maximum efficiency is 78.5%. The maximum ideal efficiency for a Class A amplifier, in contrast, is only 1/4, 0.25%. Actual maximum efficiencies are always a little lower. So these are your ideal values. Find the ideal maximum AC power output and DC power input of the amplifier in 1729 of example 17.7. Ignore the power dissipated by the bias transistor. So if we go back to 729, let's see what this will take. 729, there we go. 729. So there are our values for example 717. In the example then, IC sat was found to be 1.25 amps, 1 1/4. Thus, the power out maximum, 0.25 VCC IC sat, is equal to 1/4 times 20 volts times 1 1/4 amps, which gave us 6.25 or 6 1/4 watts. Power DC, then VCC IC sat over pi gives us 7.96 watts.